think how the book is designed in chapter 11, the sections 11, 1, and 2, we're talking, which we were doing, I guess, last Thursday, we're talking about parametric representations of curves. And if you remember, what you have a parameter if you express the x and y, thinking of graphing in a plane, if you express x and y in terms of some other variable, some third variable, you call that thing the parameter. So for example, that can be time, like we were talking last week, where you're thinking of tracing out a curve with some object that moves, and here it is at time 1 second, and here it is at time 2 seconds, and here it is at time 3 seconds, like you're flying a rocket, for example. So t is the time is the parameter, and then for each value you have an x and a y coordinate if it's in a plane, or 3 coordinates if it's in space. Okay, so now the sections 11, 3, and 4 go on talking about 2 parameters, which lead you to what we call polar coordinates. So the 2 parameters are the variables r and theta, where what you do is you identify a point you'll call the pole for polar coordinates, and then you measure in a straight line from the pole to wherever you are on your graph, and that's the parameter r. And from the pole you designate a line that coincides with the positive x-axis normally, and normally you take the pole at the origin of the xy coordinate system, so you can relate the r parameter and the angle theta parameter measured around like this to x and y. And so if you agree to doing things that way, you have the polar coordinate system for using 2 parameters, r and theta, to represent a curve. So what we call the initial ray then coincides with the positive x-axis. What we mean with the word ray, R-A-Y, is that standing at the pole, you turn through some angle, and you can go along a line tracing out what we call the ray. So if you don't stop, then your ray would be a half line from the pole extending off to infinity. And one other thing that you can do, which is a complication of polar coordinates that you don't have with Cartesian coordinates. Remember, Cartesian means xy or xyz. And that is that you could turn through the angle either counterclockwise or clockwise. And depending on which, you call the angle positive or negative. And what it leads to is that there are 2 independent systems, really, of polar coordinates, and that you can actually get more than one formula that will define your curve. They'll both define the very same curve, and yet you can't get from one formula to the other by trig identities and or algebra. And that's because you have more than the one independent way to represent a point, same point, in polar coordinates. So what you can do, as we were saying a week ago, is you can turn through the angle and then walk forward the way you're facing. That's like the green arrows. And locate a point out here, and these would be the polar coordinates. Even though turning through the angle is what you do first, when you write it, you write the angle second, and how far you walked, you write first. And that's a thing like English spelling that really doesn't make any sense, but it's what you do. And then you could also, having, say, this point in mind, you could turn through the theta and then keep going by another 180 degrees. What I have here is radians, so this could have been degrees. And then you'd be facing as this arrow indicates, and then you could back up from the pole. And that would be, if you're walking backwards, a minus r. And then the angle would either be the original theta plus pi, or you could have done the original angle and then turned back this way 180, which would have been minus r theta minus pi. However, minus r theta plus pi minus r theta minus pi are the same red system, because with either the green system or the red system, having chosen a pair of polar coordinates, you could instead modify the angle by adding any multiple of 2 pi. So minus r theta plus pi, if you come down here, you can add 2k pi, where k is any integer, and if k is minus 1, that ends up being theta plus pi minus 2 pi, so minus r theta minus pi. So whether you made this theta plus pi or theta minus pi, you're in this system, and the difference is just one periodic repeat, one full turn. So your two systems really are based on what I have over here, and then you can modify by adding multiples of 2 pi to the angle. And so with the red, you can write it minus r theta plus an odd multiple of pi. That would be the complete system. And then if k is 0, you have this, and if k is minus 1, you have theta minus pi. And then with this one, it's theta plus the even multiples of pi. 2 pi, 4 pi, minus 2 pi, and so on. Okay, but r equals f of theta, and minus r equals a function of theta plus pi, and minus r equals the same function of theta minus pi, will all do the same curve because they all do the same points, theta for theta and r for r. And you can't necessarily get from r equals some function of theta to minus r equals that same function of theta plus pi, say, by trig identities. But they are the same graph, so they are equivalent, but they're not necessarily algebraically equal. So there's a difference between equivalent and equal in that sense. If you refer back to the handwritten notes, again, is there anybody, I gave these out last week, is there anybody here who doesn't have the handwritten notes? If you refer back to those, you see I've said this, in the second paragraph on my first page, equivalent polar coordinates locate the same point, and so on. So what I just said, I've written there. Do you have the, you don't, well, you don't have that. Okay. So, and remember that another thing that we talked about last week is at the bottom of the page, the tangents at the pole. Again, as we did last week, look inside to see what I mean by that. Go to either page 4 or page 5, as I've numbered the pages. So the back side of the second sheet of paper, say. And look at the flowers, and any of the 4 that you see, that, as I said last week, I think look more like daisies than roses, but people call them rose curves. Roses are more romantic, I guess. So if you notice, if you look at the 4 pictures there, the form is either sine of some whole number multiple of the angle or cosine. And they're the same flower, a sine 3 theta or a cosine 3 theta are the same flower. It's just the one is rotated compared to the other. And again, with a sine 2 theta, or on page 5, a cosine 2 theta, that's the same flower, just one's rotated. And so if you notice in my sketches there, say the r equals a sine 3 theta, you come in, you draw, say, the first petal, and there are 2 rays. Remember, the word ray refers to this half line that starts at the pole, that would be tangents to the curve at the pole. And so you have tangents at the pole. Now, the way that you get those is what you learned whenever and wherever you took trig in the section called solving trigonometric equations. You set what they are. They are the various solutions to a sine of 3 theta equals 0. And so you think, when does the sine equal 0? Angles, say, in radians. The answer is the multiples of pi, 0, pi, 2 pi, 3 pi, and you could go negative too if you wanted. And so sine 3 pi equals 0 has solutions. 3 theta, 3 theta equals 0, theta is 0. Okay, that's your initial ray. The initial ray here has the polar coordinate equation, theta equals 0. See, and the idea is r then is anything. Walk the way you're facing. And next, 3 theta equals pi, so theta is pi over 3, 60 degrees. And you see I've labeled that ray there, that tangent, with the pi over 3. Next, 3 theta equals 2 pi, so theta is 2 pi over 3. You see the ray 2 pi over 3 in my sketch, and so on. So you keep going until you are back where you started. And so there actually are six solutions that are different rays, and then if you keep going, you're just repeating yourself. So this is handy because it helps you make the sketch, and halfway between the two rays that are on either side of one of the petals would be the center line because it's symmetric. And so then you can fill in to see that the center lines of the petals are at pi over 6 and 5 pi over 6, and the 3 pi over 2, so that would be 9 pi over 6 if you want. Okay, so that is something that's handy if you're trying to interpret the extent of one loop of a figure like that. Now we need that for the work we're doing today, which is the area, going to be the area, figuring the area of one of these loops in the petal, one of these petals, say, in a sine 3 theta. So then 3 times that would be the total area of the figure. And also, if you wanted to figure the arc length of one of these loops, the tape measure length along the curve, and you could figure one of the petals and then 3 times and so on. So to do this, you see, you have to know how your curve looks, what the figure looks like, both to get the limits that you need for your integration. You know before I say it that getting the area or getting the arc length is integrating in polar coordinates. That's where today's class is headed. And also, if you wanted the arc length or the area for the total figure, the natural thing to do is take advantage of the symmetry and figure it for one of the petals and multiply by 3 or by 4 or whatever the case is. If your coefficient in these flowers is odd, that's how many petals. If it's even, like on page 5, 2 times the coefficient is how many petals. That's a handy thing to know. Turn back a page and look at the front side of the second sheet of paper, page 3. And you see I have 16 related sketches there. And all of these, excuse me, all of these curves go by the name limaçon, which I will write for you somewhere. So that's a French word, and you see that there is this symbol in French has a name. I'm not quite sure what it is, but if you're French speaking, you know the name for the thing. And anyway, that tells you to say the C kind of through your nose. So it's it's a limaçon, not a limacon like Germans say, as a French person would say, view this. Okay, so it's a soft C. Anyway, all 16 of those are that type of curve, and you see there are different situations that you can have. You can have the inner loop. That's the form, say, R equals, if you look at the first 4 pictures, the top row with the inner loop, that's when the B is larger in size than the A, because that means that the R can become negative. And so if the R is negative, remember that what you do from last week, you turn through the angle and you walk backwards. So if you thought of the very first picture of the 16, the upper left-hand corner, you could be facing vertically in the picture, looking at the page, straight up on the page, and then if the B is greater than the A, or enough greater, the R will be negative, and then you'll back downward. You see, you turn facing up like at like on the positive y-axis, if you thought of your pole at the origin, and then because the R is negative, you'd walk backwards down the y-axis, and so you trace out this inner loop in this way. And the same is possible with any of the four orientations. And they're all basically the same curve. It's just how you turn it, and that changes whether you have sine or cosine and plus or minus. Then the second row is where the A and B are the same. So A over B is 1. So it's the same as saying A equals B. And you have what we call a cardioid, because it's a heart-shaped graph, which you can see. Then the third row, the A is between B and 2B, and so what you get is the third row type of graph where there is kind of a dent in the curve. And then if A is greater than or equal to 2B, the bottom row, you get what people call a convex limacol. So comparing rows 3 and row 4, you see the row 3 limacol is dented in, and the row 4 is bowed out, if you want to say it that way. So they're all related, all 16 of the situations, but there are these differences that are determined by the relative sizes of what I'm calling A and B. To offer you these handwritten notes as a kind of a handy little dictionary, it's even in the world with computing power, sometimes something like my little dictionary is handier and faster than firing something up and entering the formula and all that. You can just kind of look at it. I mean, like this page with the 16 limasols, you can take the whole page in at a glance and so on. So then let's look at the sections 11. Well, let's see, let's look at the maple a little bit. So if you look at the maple that I think everybody now has for today, you can get maple, and therefore you could get one of the other computer algebra systems to draw curves in polar coordinates. In using maple, there are two ways that it knows if you're doing polar coordinates. Either you say coords equal polar, or you have the command polar plot, which I will show you when we turn the page. So as I say there, the command polar plot applies when we have r as a function of theta. And if you want to, you could use a letter like t instead of theta, as long as you say coords equal polar or polar plot. Maple would know that that's the angle. For sometimes, if you have your curve defined as an equation, you would still use implicit plot, and you could also get the graph correctly if you, in some cases, by doing things parametrically, as in section 11.1 and 2 that we talked about last week. So, for instance, the first one I have, implicit plot, if you want to use the Greek letters, either you can go to a palette if you have a modern version of Maple and use the mouse and click on the appropriate Greek letter and it will enter in, or you can spell the thing. So like theta equals pi over 6, I spelled out the theta, and pi you spell as capital Pi. So what I'm trying to do is to draw the ray that's at a 30-degree angle with the initial ray. So theta equals pi over 6, and then the r would be an extent, say -5 to 5. How far are you going to walk? And if you do implicit plot, you'll have two variables, the r and theta, the two parameters, and you have to give some kind of limits on each of the two parameters. So if you give theta limits like -pi to pi, that puts you just on a line, you see, because you're thinking parenthesis minus pi, comma, dot, dot, pi, parenthesis. All it leaves you is just that one line, and coords equal polar. And so you can see how you can draw a ray that way. Another way you can do it, if you look at the second picture, I'm using t instead of spelling out theta, and then at pi over 6, so and then -5 to 5, and you see that'll do it. And then the next thing, look at something like problem 13. This is a curve that we call a lemniscate. I have the lemniscate in my handwritten notes at the bottom of the back side of the first sheet of paper, if you notice down there. And there are 4 pictures there. They're all the same ribbon tied in a bow, which is what the lemniscate name means if you go back to the Latin. And it's just how you're holding the bow in your hand, how you're orienting it. So implicit plot then, you see it's implicit plot because you have a relation. You have r square equals in your formula. So 4 cosine 2 theta, and again I spelled out the theta, and then r is -2 to 2, and the theta is 0 to 2 pi. Coords equal polar, and with implicit plot, to get a good drawing, sometimes you have to make the computer calculate a lot of points, because it's in your picture, it's working the same as a television picture, where you depend how good it is depends on how many little pixels you light up and so on. So that's what the num points equals 5,000 is about. That's for the number of points, you see. And then you can put a title on, as always, and you can turn the page, and you see the curve that looks like the one that I drew and called r square equals a square cosine 2 theta, like the one I drew by hand. Okay, and then problem 14, you see, is this thing rotated. And just to show you that the num points was in there in 13 for a reason, you see in 14 I didn't say 5,000 points. And you get the general outline of the picture, but you see how the line segments appear on the actual boundary. That's because to make it look like 13 smooth, you have to take more points. So that's something that happens with the implicit plot command anyway. If you do polar plot, which is your alternative when it's polar coordinates, what you always get is what you see in the picture for number 17, and that is you get this polar coordinate background. So what Maple does with polar plot is it makes a picture that would be like what you had if you had bought polar coordinate graph paper and then drew the graph. There is such stuff, you see. In the world before computers, people would go get polar coordinate graph paper in the bookstore and so on and draw the things on that background. So polar plot puts that background in, and that doesn't hurt anything, certainly. You can see the curve. It's a cardioid that where the long axis is along the initial ray. So that's your one, well, it's -1 plus cosine, because that's the way problem 17 is given. And you see it's also, if you compare it with my page 3, it's the same picture as I have on the second row that I called 1 plus cosine. So -1 plus cosine and 1 plus cosine are actually the same graph. That's this equivalent curves. You see, there's more than one way you can write the same graph using polar coordinates, and that's back to this business. And I have a little bit about that on the board there. Well, as you can see, I've drawn problem 17, and I've drawn it. I've used different sets of commands. If you see down there, I say if you don't like polar plot, you can set up the problem for the parametric plot. And if you notice, what I have is plot -1 plus cosine t, t equals 0 to 2 pi, and then say chords equal polar. And you see at the top of your second sheet of paper, the top of what's page 3, you have that same thing without the polar coordinate graph paper. And you can use implicit plot and say chords equal polar, and you may get it with implicit plot. You have to put limits on both variables that you name. So you have to have limits on r and limits on the t. And again, you better do the 5,000 points to get a smooth graph. But, So there's, what I'm showing you are alternatives that are available if you were graphing with Maple. And then I show you -1 plus sine t, and you notice that this is the one that's in the middle of the page on what would be page 4, the back side of the second sheet of paper. And you notice that's the same picture as 1 plus sine if you compare with my dictionary here. And then I have the r equals cosine 2t. So there's 4 petals to the daisy with polar plot. Well, let's see. I have, first of all, I have the sine 2t with polar plot, and then I have the cosine 2t, top of the next page. And so number 19 and number 20 are really the same flower. It's just a matter of it being rotated. Okay, and so I have various pictures as you look on through here. So let's over here and look at some things. Another thing that you can do, which is what we're taking up in problems 17 through 20 in the homework, is find the slope of a polar curve when it's defined r equals f of theta. So if you were here last week, exactly a week ago, we were doing graphs expressed parametrically with one parameter t in section 11.1, and in section 11.2 we were calculating the slope, the first derivative dy dx, and also the second derivative, which would tell us if the graph was concave up or down, indirectly is related to calculating the curvature. I was talking about curvature, the second derivative a week ago, remember. So these problems are the equivalent if you're talking about representing your graph with the 2 parameters as in polar coordinates. So these problems want the slope of the polar curve defined, say, as r equals f of theta. And so, again, I use m for slope, as we did last week. And as a function of theta, first of all, it is dy dx always. And using the chain rule, that's dy d theta over dx d theta. This is just like section 11.2, where it was t and dy dt over dx dt, if you think back. So the difference now is that we don't have x and y in terms of just one parameter t. There are 2 parameters, the theta and the r, where the r is f of theta, which has to be given. You have to know that to know what problem you're doing. So you're doing for dy d theta, y is r sine theta. That's because of right triangle trig. You see, if we take the pole at the xy origin and the initial ray along the x-axis, then we can draw the right triangle like we did last week and you have R on your hypotenuse, and X and Y, and then right triangle trig, gets you the parametric representation of X and Y with two parameters, R and theta. So that's how come f of theta sine and f of theta cosine. You could think R here and R there if you wanted. So then your M is this derivative over this one. See, this is product rule, and so is that one. So product rule, and derivative of the left-hand factor times the right plus the left-hand factor times the derivative of the right, and the same down here. Remember, the derivative of the cosine is minus the sine. So this is your formula for the slope as expressed as a function of the angle theta. And of course, this will become undefined if this happens to be zero, which it could be. In other words, you'll have typically a vertical tangent. You can see that you would here at this point on this cardioid, for instance, and you would in the same way on the Leibniz gate. You would in the same way at the end of the petal on the flowers if it's cosine, R equals 2 cosine theta or something like that. So now looking at this same problem 17, we looked at the graph of 17 with the maple, and notice that minus 1 plus cosine theta is minus 1 minus cosine theta. So in turn, if R is minus 1 minus cosine theta, you can multiply here and there by minus 1. So minus R is 1 minus cosine theta. So then this is an alternative way to think of the problem as they gave it. And so then you can say that minus R and f of theta plus pi or minus pi will be the same graph as R equals f of theta. So there are two ways, in other words, that I've numbered here, 1 and 2, that you can reinterpret just how this graph is to look. So one way you could look at it, if you write it like this, if you compare R equals f of theta and R equals minus f of theta, the one is the reflection through the pole of the other graph. So this is the reflection through the pole of the graph that is defined by the R that's in the brackets. See, I'm thinking of R equals f of theta and the R equals minus this thing. Well, the relationship between this and R equals minus something is the reflection through the pole. So what you start with here is the reflection of this graph, and if you look at my sheet of paper, you can, with the 16 cardioid limassol graphs, you look at line 2 again, and you see the R equals 1 minus cosine theta graph is the second one in, and the R equals 1 plus cosine is the fourth one, and they are each other's reflection, in a sense, through the pole, if you just compare the two pictures. So That's one way to say that this thing actually is going to look like this, which you find on our sheet of 16 pictures as 1 plus. And the other way you can see they're the same thing. This graph, which looks like that, is the same as if it were minus r and you change the angle into either theta minus pi or theta plus pi. That doesn't matter. That's the equivalent polar coordinates of this. It's not that you can take trig identities and start here and get to where we're going, but it's because of the equivalent ways you can write polar curves, because different ways r theta and minus r theta plus phi are the same point. So then do your trig identities. Cosine theta minus pi is cosine theta cosine pi, and then plus sine theta sine pi. Sine pi is 0 and cosine pi is minus 1. So it's the same as minus cosine theta. So now minus r equals 1 minus cosine theta, and r equals 1 plus cosine theta have the same graph because of this business. It's not because of trig identities, it's because of the equivalent points that I can stand here and turn through theta and do this, or I can stand here, theta, and then pi, and then do this. See? Notice how clever I am. I have the wall here, so if I go too far, all I'll do is hit the wall. I won't fall down. Okay? So, anyway, you can think of it that this is how the graph looks. Or you could simply take a computer system and enter the thing in and let it show you how it looks. So what we're after is the slope here and the slope here. That's what problem 17 wants. Okay. So at pi over 2 and r is minus 1, or at 3 pi over 2 and r is minus 1. You see, if you start here at the pole, you turn through pi over 2, you're facing that way, and then if your r is minus, you walk backward, so you end up down here. If you stand at the pole and turn through 3 pi over 2, you're facing down, and then you walk backwards to minus, so you end up there. That's the way they gave the problem, so I'm showing you where you end up. If you thought of this simply as r equals 1 plus cosine, then turn through pi over 2 and walk the way you're facing would put you there. And turn through 3 pi over 2 and walk the way you're facing and you get down there. That would have been an easier way to ask the same question. But given the way the book gave the problem, which is like this, and the way they gave the points, I can show you that these are the places you want the slope. And it works either way. So if you take the problem as they gave it and do the derivative of cosine, you get minus the sine, and then you substitute into this, so you have your f prime, so that's your minus the sine times the sine. This is your doing your product rule derivative, and then you have your curve as it's given, and the derivative of the sine, which is the cosine, there. So all I'm doing is substituting into this formula here either what is your f of theta or what is your derivative of it. So I get all of this stuff. Then I put in pi over 2. Well, sine is 1, so I get minus 1, 1. This from the formula, cosine of pi over 2 is 0. Cosine of pi over 2 is 0. Then I get minus 1, 0, minus 1, and cosine again is 0, and then the sine is 1. So do your algebra here, and your slope at pi over 2 is minus 1. Let's see, and that theta equals pi over 2, using the graph the way they gave the problem, you're down here. So the green here goes with the green line. And then you can do the same thing again up here that goes with this line. And again, you can see that slope 1 is right in the picture, and that's what you get here. In section 11.5, we want area and we want arc length, which we'll take up now, but I'd better do this. So to see how we do the recipes to get area and arc length, you can go back to thinking of a circle where you know the formula for area and for circumference, which is arc length. And so looking at the area formula, if the differential area is a half r squared d theta, then when theta runs 0 to 2 pi for a full circle, you see you'd have a half r squared d theta integrated 0 to 2 pi, so you'd have theta. So you'd have a half 2 pi r squared, and that gives you the right formula. So that's a way to remember then that your, in general, your formula for arc length is, or pardon me, for area rather, is going to be the integral of the differential area, which is a half r squared d theta. Now, if it's not a circle, the r is going to be variable. It's going to be your function of theta. So for general curves f of theta, your dA would look like this, and your a would be the integral of the squared polar coordinate function that defines your curve, integrated with the angle. And if you want a portion of the curve, the angle goes from alpha to beta. These are the Greek letters alpha and beta that I defined over there for you. For arc length, say script letter L, we think of the differential arc length, ds, from the same kind of thinking that we did first in chapter 6 when we were talking about arc length. And the squared, there it would have been ds dt, for example. ds d theta square then is dx d theta square plus dy d theta square. That's your differential triangle. And what we have now is that x and y that we have here are expressed with the two parameters. So again, if you want dx d theta, you have the same product rule thinking that I have down here. So you have this same expression again, and if you want dy d theta, you have this same product rule and this same expression. So you could say I take this one and copy it there, only I wrote it as a differential quotient instead of the f prime, and the top one I have here. And again with the differential quotient instead of the prime. But it's the same product rule here that I used back here. So then I square these. So this, you can think of taking this and writing it down again in FOIL or whatever. So you're going to have the r square sine square, and then you're going to have this minus r sine times this twice. So minus 2r, I wrote it now r prime because it's easier, and then sine cosine, and then I'll have this term square out here. And then I do the same with the dy d theta. And they are here, and you notice if you add these together to get your ds d theta square, the r square will be a common factor when you add in this column, and then that's 1. This and this product are the same with opposite signs, so they're gone when you add vertically this to this. And over here, this is a common factor. And again, you have sine square plus cosine square. So this simplifies to what would be the r square plus r prime square. And instead of writing r, I wrote it as f of theta, and here I wrote it as f prime of theta. So this would be your differential and arc length, and then the arc length itself, L, is the integral of this differential arc length between the limits on your curve, alpha to beta. So what you integrate is the square root of the square of the formula for the curve and the formula for the derivative of the curve. And so we'll finish by doing a problem where we use this formula, and by doing a problem where we use the formula for differential area that we integrate to get the area. So take a look, for instance, at problem 3 of 11.5. So we'll do that in just a second. You see, this is what I call a convex limosol, because this number is enough larger than this number so that the r never can be negative. There are angles where the cosine can be negative, but the most negative it can get is at minus 1, so then the r is still 4 plus 2, so there's still a positive r. You're still, no matter how you turn, you're going to walk forward. So you're not going to have an inner loop, and when the r when this one is greater than or equal to 2 times that one, you have the bottom row in my picture of 16 pictures of a limosol where it's bowed out. So if you want to, you notice that your formula that you use for area is, forgot the half. You're going to have 1/2 the r square d theta. And I'm going to use symmetry. The curve, actually, the theta would go 0 to 2 pi, but if you use the symmetry of the picture, you could take the top half, 0 to pi, and double it for the area. It's always to your advantage to know how the curve looks and use symmetry. It's especially so in the last example that we'll do. So I use the 2 for symmetry, the half, because you need that half so that your area for a circle will be pi r squared. You want to look at it that way. And those cancel. And then there is a 2 in as a factor in the formula, so I factored it here. Notice that it's still in the brackets because it's squared, because the formula is a half integral of r squared. And so I take out this 2 squared, there's the 4, and then I'm squaring this, so I have 4, and 2 times 2 is 4 cosine theta and cosine squared. And so I'm integrating 3 separate terms. Because of the relationship between 2 cosine square and 1 plus cosine of 2 theta, I decided to take one of these 2's. I have 2 of them here because it's squared. I take 1 back in. So I wrote 8 and 8 and 2. So I could replace this with this right here. The other 2 is still out in front. Then I integrate 8 to 8 theta, 8 cosine to 8 sine, and then this I can replace with 1 plus cosine 2 theta. And then I integrate that, and I get the 1 becomes a theta, and cosine, I get sine 2 theta over 2. And then I evaluate all that 0 to pi. Sine pi is 0, sine 2 pi is 0. I have 8 and 1 are 9 pi times 2. So that's what the book says it is. Okay, now the last thing I want to do is the arc length. And again, I will use a symmetry argument, and it's very important in the arc length problem. Looking at this same recipe box, 2 cosine square is 1 plus cosine of twice the angle. So if you gave this angle a name, we'll call it T, 2 theta is T. If this is T, then this is half of this, so then this is T over 2. So the double angle formula here is also a half angle formula. If you want to call this T and this T over 2, and instead of standing this way and reading this way, I stand over here and read this way, you see. Here's my angle and here's my half angle. So anything that's a double angle formula, if you stand in one direction, is a half angle formula if you stand and look at it in the other direction. Okay. So, let's see, where am I? Okay, over here. If you look at problem 23, it wants the arc length for 1 plus cosine theta, which looks like this, and for the whole curve going clear around. So the first thing I do is my symmetry argument. The top half is symmetric with the bottom half, even though my picture isn't that well drawn, but it's supposed to be. And so I say 2 and 0 to pi. And then I look at the recipe over there for arc length, which is here. I take the square root of the square of my f of theta, which would be my 1 plus cosine, and the square of my derivative, which would be minus the sine. See, I have them right here. So I'm squaring this, that's these three terms. I'm squaring that, and minus times minus is plus. And then sine square plus cosine square is 1, and that's another 1. So that makes 2 plus 2 cosine theta. And then I can take the common factor 2, which is under the square root sign, out. And then I have the square root of 1 plus cosine theta. And then I go to the recipe box and read in this direction. 1 plus cosine is this 2 cosine square, because I'll have a square root of a square, you see, like this. So I get another square root of 2 out of this. I have this one, and then I get another one out of that. So then look at the square root of cosine square. The square root of a square is always the absolute value. This is where this problem can become tricky, because the absolute value of a number is the number if it's positive, and it's minus the number if it's negative, right? The absolute value of minus 2 is supposed to come out 2. And how do you do it? You say it's minus 2, right? So, if you have used the symmetry argument, so you're working on the top half, 0 to pi, then if the limits are 0 to pi, then theta over 2 is going to go 0 to pi over 2, and the cosine is positive, and the absolute value of positive is the cosine. If you did not do the symmetry argument, if you went 0 to 2 pi, then when you're between pi and 2 pi, your pi over 2, or your half the angle would be between half of pi, which is pi over 2, and half of 2 pi, which is pi, and your cosine is negative, and your absolute value would have a minus sign on it, okay? Well, I'm staying away from that by using the symmetry. If I do this and say that the absolute value is the cosine, see, I have 2 here, and these make another 2, that's 4. Then I integrate cosine, I have sine theta over 2, so over a half. Because of this 1/2 here, I have to divide by it. And then 4 divided by a half is 8, and that's what I want. But if you try this integral, if you go 0 to 2 pi, and you ignore the issue of absolute value and just take cosine theta over 2 and integrate that, you'll get the 2 sine theta over 2. You put in your limits, and you'll have sine of pi, which is 0, minus 0. And you'll be saying the arc length is 0. And you know it isn't. But what's happened, you see, is you miss the fact that you have to take into account the absolute value. You either have to use the symmetry argument, or you have to split up your interval to where the absolute value is cosine 0 to pi, and then minus cosine pi to 2 pi. So these things can become tricky. One last thing that I guess I didn't go through with you, in the 11.3 section, they want us to convert from polar to Cartesian coordinates and identify the curve. So 27 in 11.3, you have r cosine theta is 2. So your parametric representation, the right triangle, is x equals r cosine theta. So this is x equal to. So here you are Cartesian, and you recognize that's a vertical line. So your vertical lines would look like this. If you preferred, r is 2 over cosine, or is 2 secant. So r equals 2 secant theta in polar coordinates is a vertical line. And in the same way, if you looked at something like this one, r equals 4 cosecant theta, cosecant is 1 over the sine, and then r sine theta is 4, and you see that's y equals 4. So a horizontal line like y equals 4 becomes r is 4 cosecant theta. So you use secant and cosecant for vertical and horizontal lines. Notice if you have a thing like 36, r square is x squared plus y squared. It's the hypotenuse, law of Pythagoras here. And your r sine theta is y. So this is a kind of circle. And to identify the circle, what you do is you take this across, and then you complete the square, as they say it in algebra. You should have suffered with games like this in Math 108, probably, or Math 143, or in high school. So you take, when this coefficient is 1, you take half of this and square it. So half of minus 4 squared is 4, and add to both sides. And then these three terms are a square. So you have x squared plus y minus 2 squared is 2 squared from here. And that's a circle with center at 0, 2 with radius 2, like that. So then notice the 13, which we started with looking at our maple when we were first looking at it, is this lemniscate. And if you wanted the tangents at the pole, you'd solve cosine 2 theta equals 0, and you get these 4 solutions, and then you repeat yourself. So that covers pretty well everything that's in the work. What we will do tomorrow, the next section, 11.6, reviews conic sections in Cartesian coordinates, which you have suffered with either in high school or in Math 143 or Math 147. So we'll review that, and next week we'll work with conic sections in polar coordinates, which is more complicated. But it's really quite important, because polar coordinates are how you would think of conic sections if you're flying things like satellites around the Earth, or if you're doing astronomy and thinking of orbits of the moon around the Earth or the Earth around the sun and so on. So that's what remains in chapter 11 until vacation. Vacation's week after next, which I'm sure you know. And then after vacation, we'll spend all of our time on chapter 10. So just a kind of preview. So I'll be glad to take test 3 from you if you've done it, or you can bring it tomorrow.